Okay, good afternoon, Anna, everyone. Good afternoon. Yeah. Right. Then I think, how you felt yesterday's exam, Anna? How you felt yesterday's exam? Able to hear my voice? Able to hear? Yeah. Voice is no, low, no, I think. Now it is clear. Paper was medium. Okay. Right. It's audible, right? Okay. Able to solve the questions from my track? Uh, but your questions were easy. Okay, thank you. Right, then no problem. Able to solve. Okay, then thank you. Right. Good. Who wakes at little bit hard? My part, your questions are easy. Okay. Oh, straight line, motion a plane were easy. Okay, right. Okay, anyway, you tried and felt a bit easy and medium. Okay, paper was medium. Right. No problem. We will improve. I think first time you wrote my objective exam from my track. This was the first exam. Yes. Yeah, previously you wrote the exams on SARS track only, not from my track. Yeah, more SARS. Yeah, first time. Yeah. That's what I'm saying. So anyway, not bad. Okay, it's a good sign, right? Then okay, here yesterday not yesterday, in the previous class, so we completed some part about I think normal reaction. Okay, and concluded that normal reaction is actually the property of both. Okay, so it is the property of both who are in contact. Right? Am I right, Nana? Is it a property of only one or both? Normal reaction which is perpendicular to the surface. Yeah, both. So on the red color block, I have to draw in free body diagram. It is the direction of normal reaction. Yes, it is just like wife and husband, Nana. It is the property of both. Okay, otherwise court won't accept. Okay, the earning is the property of wife and husband. So here normal reaction is also property of both red and black. Okay, so the normal reaction on the other will be here like this. Downwards normal reaction is on black or red. This one, what I pointed here, this is on black or red normal reaction. On black or red. Yeah, this is on black. Very good. And this one N on, of course, red. Good. So likewise, we have to draw two normal reactions at the point of contact. Sorry, at the line of contact. This is the line of contact. Okay, good. Right. Here, that normal reaction property, what you told, really have to take on both. Okay, to solve the numericals. Is it important, sir? This concept, taking the property of both. Yes, it is important. Otherwise, you can't solve few problems here. Say one example, sir. Really where it is important, sir. Yes, sure. Come to here. Already I gave an example on the inclined plane in the previous class. I think you got some normal reaction like here, and it is n sine theta and n cos theta. Remember, Nana? Yeah, good. So this n sine theta results to here pull this block, sorry, wedge backwards. Yeah, wedge problem. Yeah. This one already I gave what I remembered. Am I right? This one given or not, Nana? In the previous class. Yeah, given. So here, right. Already I gave one example, the importance of that normal reaction taking on the other body also. And one more here. Okay. This one actually we call it as painter model, Nana. Means how they paint the outside walls of apartment or tall buildings. Okay. Usually at the terrace, they fix one support. And from the support, usually they connect one pulley. Here, this is one pulley, they connect. And from there, they hang the rope. Usually for our physics, we consider they are massless ropes. Neglecting the mass passed over the pulley and taken here like this. And one painter we see in a box or else on a wooden stand. Okay, I consider he was there in a box, like one cage. Okay, this is a cage, and the other one part is connected to the cage here, fixed, like how we connect the lift in the apartments to the cable. Here, one part is connected to the cable. Other part is passed through the box, closed box here. Of course, this side is open. Otherwise, how can he paint the wall? This is the wall of apartment. Okay. Of course, this side is open. Okay, Nana? So if you want that, then I will open that part here. No problem. That's not a big issue. I will open. This is open. This side is open. Okay. And he can paint the wall if his cage is close to the wall. So here I am taking one person inside. He is the person. Inside stood, and with the hand, of course, with laughing face, okay, holding the rope. Okay. So where is the other hand? Don't ask. Okay, this is the other hand. Okay, right. Here, that person holding this one with a single hand, and here he can pull this cage either up or down by pulling this rope or releasing this rope. Suppose if he pulls this rope down, the total cage along with the person will go up. Am I right, Nana? If he pulls this one downwards, the total cage, of course, in the case, person is there. Person and cage will go up. Am I right? Yes. So that he can move to the next upper storage. There he can paint the wall. Suppose he forgot painting the first floor. Okay. Again, he will release the rope so that he will come down like this. And where he forgot that part, he can fill with the paint again, first floor. So by pulling this rope downwards or releasing the rope, he can move up or down with some acceleration. Suppose the acceleration with an acceleration or two cases here, either up or down. Okay. While moving, the question is, what are, number one, the tension in the string, and number two, what is the normal reaction between the person and cage, that is box. Okay, we should not call it as cage. Why? Because he is not a bird. Okay, so we better say it is a box. Okay, in this example here, you can understand what is the importance of the normal reaction. Okay, keep in mind all the times the hand is horizontal. This is the hand that is always horizontal. Means keep in mind, suppose he is pulling the rope downwards, the downward force is equals to here the tension. That's what I'm saying. Is equals to, if he tries to pull this rope downwards with a force F, okay, then F is equals to T. That's what I'm saying. Understood that point, Nana? Clearly I write here. If he pulls the rope downwards, with a force of F, then to keep the hand horizontal, neither moving up or down, horizontal, okay, the tension in the rope or string, rope I told here, no? Okay, right, in the rope, equals to, that is a T, nothing but T, representing letter, I write here, T equals to F. Will you accept this point, Nana? The applied force, with what force he is trying to pull, that much tension will be created. Will you accept that? Say yes or no. Yes, with how much force he pulls, that much tension will be created at the hand. Yes, okay, right. So I think first question answer is over. What is the tension in the string? Simple, with how much force he is trying to pull this rope downwards, that much tension will be created. So first question answer is over. Okay, right. Consider it is massless string, massless rope. And as usual, it is a frictionless pulley. Okay, good. It means following our conditions. Now here come to the free body diagram to understand the importance of normal reaction. Yes, FBD I am drawing here. This is the cage. Okay, one side is open. Yes, and here is the person. Oh, he is the person here, free body diagram. And holding the rope like this. Okay. Is it clear, Nana? All right. Of course, again with a smiling face. Yeah, good. And here on the person and on the cage, what are the forces? Okay. Take here mass of cage. Better I write down here. Mass of this box is equals to capital M, and mass of person, I am taking it as small m. Now I think one force on box and person you can say. Who is that force? Who is this? Or who is this, right? If you know the mass, who will act downwards? Ah, weight, because of weight. Yeah, good. Why you are taking this much time? Again, Thursday fever. So mg and this is mg. Weight of the person, weight of the box in free body diagram. Okay. Number two, the box is connected to the string. Okay, connected to the string. Here, this is the tension in the string by this rope. And this hand is not connected to the box. Here passed through a small hole and he holds this rope. So at the hand, there is again some tension here. This is tension on the box. This is the tension on the hand. Okay. And number three, who is the third force here? Keep in mind, he is in touch with the bottom of the box. In touch, in contact. So who will be the normal reaction? Very good. Normal reaction on the person. In what direction? Upwards or downwards on the person? Normal reaction, correct. Up or down on the person. Who is above the other? Box is on the person or person is on the box? Man is on the box. Okay, very good. So here man is on the box. Okay. Correct only. Man is like red here in this example, in the concept. Man, the red is on the box, black. So it is appeared like a man, it is appeared like a box. So on the man, normal reaction acts upwards or downwards? Up. Why you told previously down? That is up or down? Others are not responding, means that they did not understand, I think. Understood? Yeah. Up. Very good. Very good. So it is clear. Now on the person, it will be understood. Good. Upwards. Nothing confusion there. Towards the man, it is the normal reaction. And on the box, it should be same, but in opposite direction. This is the normal reaction. This is N, this is N. Okay. So all together, three forces here, three forces there. Okay, in FBDs. Okay. So from the FBD, we check. This is the case what we are discussing, going up. So here it is going upwards with an acceleration. Means person is also going up with an acceleration. This is the acceleration what we are considering. If we consider this is the case, upward force should be greater or downward force should be greater? If it moves upwards with an acceleration A, moving upwards. Very good. Very good. Upward force should be greater. Upward force should be greater means T minus mg minus n is the net force. Correct, Anana? Upward force is right. Good. So upward force is greater, T minus mg minus n here is the net force. And here T upward one more is there, plus n opposite direction minus mg is the net force. Are the two equations correct, Nana? What I wrote on the board? Or any mistake? If any correction is there, you can say. Correct. Okay, right. Is equals to net force is always equals to mass into acceleration. This is the net force. Correct, right, good. Here, net force mass is small m. Mass into acceleration is the net force. Okay. So we wrote the two equations. That's it. Okay. Already I found T. So from the two equation, not required to find out T. I require N. Okay. But to find out N, first I require A. That's why I'm going to calculate first A. Take it as equation 1. Take this as equation 2. Very good. Then first eliminate N. Eliminate N means I have to add 1 plus 2. Two equations I'm adding here. So T plus T, 2T minus mg, n plus n cancel, minus small mg is equals to adding right hand side ma plus ma. Okay, so I am getting here on the in the next page. That implies 2t minus g common m plus m is equals to right hand side a common m plus m. Is it correct, Nana? What I wrote? Minus g common m plus m, correct? A common m plus m, correct only, I think. Right. Not 2t minus g, Nana. Here, if you divide with m plus m, by taking this m plus m to the other hand, I will get 2t by m plus m minus g, m plus m cancel equals to a. This is what I get. Acceleration. Okay, right, good. This is the equation what I got here, Nana, to find out the acceleration. But he did not ask the acceleration. He asked the normal reaction. So substitute this A either in first equation or second equation. That is your wish. Okay. Suppose if I substitute in the second equation, that implies T plus N minus mg equals to small ma equation 2. In this, I substitute a value here. Therefore, n is equals to ma plus mg taken to the other hand. Okay, minus t. Okay, from this substitute a value, that is mg plus m into a is 2t by m plus m minus g. This is a value minus t. That's it. This is n value. I am not interested to simplify that equation. I will keep it like. That's it. Simply I will keep it. Okay. This is the way how to solve such type of questions here by considering the normal reactions on both person and the box. Now you understood the importance of this one, Nana? The normal reaction here. Do you have any doubts? If you have, you can post or you can ask. No doubts? Okay, Pakka. Right. Good. I think long back, I don't know who, Lakshmi Gayatri, I think. Lakshmi Gayatri posted one question related to this one. Now, will you solve that question on a Lakshmi Gayatri? Long back, I think you only asked if I am correct. You only this type of model asked, posted to me personally. Is it you? Yeah. Good. So I think now you can solve this type of question. Okay. Will you try? Ah, okay, right, good. Then it is okay. So here, this type of model is also over, Nana, and this is, keep in mind, very important model. Okay, called as painter model. This painter model is very, 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 very important. Okay, and next concept here. Suppose, like this is one surface, like mat, Nana, doormat or mat, what we use in the houses. Okay, and unfortunately, one of our enemy came to our house. Okay, he is the enemy. Okay, here while entering, he stood on the doormat. Okay, and says hi to us. Okay, after standing on the doormat. His intention is he wants to clean his legs before entering into your house. Okay, and you also said welcome and pull the doormat. If you pull the doormat forward in this direction while saying the welcome to the person, okay, then what happens to the enemy here? What happens, Nana? He will fall, sir, and still he is there in attention. He can say goodbye. Otherwise, yeah, good. Yeah, he will fall. You are not saying in what direction. Yeah, that is correct. He will fall back or forward, hurt and all. Okay, right. He will fall front or back. Falls to his back. If you pull the door mat here, this is the mat and he is the person. Yeah, back. If you pull the mat forward, the person will fall backwards. Okay. Now the thing is, actually, according to Newton, without apply, unless and until you apply the force on the person or an object, the object should not get any acceleration. But actually, you did not push this person backwards. Okay. Without applying the force, how he fell back? Understood my question? You just pulled the mat, not, you did not touch even the toe of this person. Legs are in contact with the mat. Very good, Shrestha. That's why if you pull the mat forward, the contact part moves forward. According to inertia, above part can't move forward. We lose the balance and fall back. Oh, what is there, Nana, to explain it again? Simple daily practice, doormat, person, pull, he fell back. That's it. Doornala. Understood? Simple. Mat, person, stood, pull, fell back. Okay? Yeah, it's simple. 5 words. Question. Concept. Good. Here the question is, you pull the mat without touching the person. The person fell back with some acceleration. Okay? My question is, without applying the force, how he fell back according to Newton's? For that, here Shrestha gave one answer. Sir, even though you are not applying on the force on the person directly, okay, indirectly, the part in contact with the mat, what the legs, in contact with the mat, you pull forward. This is what we say, pulling the legs indirectly. You pull the legs, okay, then he fell back. Now you understood, Nana? Or any queries here? Any doubts? Understood. Rachuri. Okay, no doubts. Right. Here, because of that acceleration, means if you pull the mat with an acceleration A, the person is also getting the acceleration A backwards. Okay. By that, he is feeling a force that implies the person feels, this is just a feeling, feels a force of mass of the person m into the acceleration whatever you are getting A in the backward direction. Backward direction, that is opposite direction of mat. Okay, in what direction the mat moves, for that opposite direction he falls back. Okay, better rate of motion of mat. Okay, so this type of indirect force, not direct force, indirect, pulling the legs. Okay, this indirect force, okay, that implies the indirect force. No, he won't fall, friend. If you pull the legs, obviously, what is this? Deepali, sometimes we have to practice pulling the legs. Okay, na? Okay, indirect. Yeah. Don't try to pull the legs of anyone in your daily life. Okay, it's very dangerous. Ah, okay. Indirect. The indirect force acting. Maybe. That's very dangerous. That's what I'm saying. Indirect force acting on the person is called, we are giving some name to that indirect force due to the motion of the surface in contact. Okay, this is the surface in contact. Okay, due to the surface in contact, motion of the surface in contact, what the person feels, okay, is called as, that force is called as pseudo force. Okay, this is also very important concept. It is called as pseudo force. It is called as pseudo force. Very important subtopic. What, Madikanta? If you pull the mat forward, the person will fall back. Suppose simple, Nanas. You sit in a bus, suddenly bus starts, then you try to fall back, our friend. Yeah. Then you experience it, but saying the wrong answer, na. The man falls. Okay. Suppose you are in the city bus. You are in the city bus. Okay. All seats are only reserved for girls and ladies. So you stood and seen the colors. Okay. Then at that time, suppose the driver starts the bus. Then you fall back or front. Respond. Back. That's what I'm saying. That kind of force, what we feel in city buses, is also called as pseudo force. Okay. When we fall forward, when he applies the brakes, okay, like in Telugu movies, we break the front glasses and fall on the road. Okay, when he applies the brakes, we fall forward. When he accelerates, we fall back. Okay, good, right, nice. This is what the pseudo force done. Okay. Sir, why you took this much time here to explain one small concept of pseudo force, sir? Okay, the direction of assuming the pseudo force is very important while solving the problems. Number two, not the same force is acting on the person, same acceleration is acting on the person. You observe my diagram, you can understand that. I wrote not F and F. I wrote A and A. Now you identified the difference, Nana? Identified? Yes, good. So in numericals also, we have to take same acceleration, not the same force. After getting the acceleration, multiply with the mass of that person. Okay. Now I will check litmus test to what extent you understood here the concept of pseudo force and normal reaction. Both are there on the board. The two concepts, to what extent you understood. Okay. Coming to one example here, I take in the next page better. Suppose this is one inclined plane. What I'm taking here, this is the inclined plane. And it is the inclined plane what I'm taking, and placed on a smooth surface. This is the smooth surface. And the inclined surface is also smooth. Every surface is smooth. Okay. No roughness, no friction is there. And here on the inclined plane, I placed one block. Okay, this is a block. Whose mass is small m, wedge mass is capital M. Since it is smooth, immediately after placing, it slides down. Okay. When it slides down, what happens? In the previous class, we discussed. The wedge moves back or forward, Nana? What we discussed in the previous class? Back. Wedge moves back. Wedge is moving means the person is on the mat. Person is small m, mat is capital M. Mat starts, suppose, moving back with an acceleration A. Suppose with an acceleration A, then will that small m feels the pseudo acceleration or not? That is the question. If it feels, in what direction? Answer to my question. Means, okay, I will give the options here. Means what you are trying to say, it will feel, small m feels the pseudo acceleration in this direction, option 1, or in this direction, option 2, or along the inclined plane like this, in this direction, option 3, or in this direction, option 4. Which option is correct? First, second, third, fourth. Out of the three, which option is correct? Pseudo acceleration. Ishan, I think today it is not your day. What, Lakshmi Gayatri? What you understood from this concept? You get the pseudo acceleration exactly in what direction? Yeah, Tanisha is correct. Amog correct, but he put the question mark. Why? I don't know. Manikanta, this time Karapodi said correct answer. Good. Ishan, look at the concept. Sham. Yeah, Varun is correct. Yeah. Simple, Nana. Nothing there to confuse. Simple. Suppose mat moves towards the right along positive x-axis, you will get pseudo negative x-axis. Quite opposite we have to predict. Now I think all are posting same option. So which is correct? It is moving along x-axis. Ah, okay, right. No problem, Nana. Yeah. Now I think Ishan finally got the correct answer. So understood, Nana? Which one? Quite opposite to this one means the second option is quite opposite. Yeah. Now is it correct, Nana? Ah, right, right. Good. So finally, we are getting some pseudo acceleration on this. Okay. Now it is the time to say quickly what are, why? Because it is already 3:14. Quickly, you have to say the two here, even though I think it may take 2 or 3 minutes more, you have to spare. Okay. Why? Because I can't complete in 1 minute this part. So you have to spare and don't remind the time. And here, look at, yeah. Ah, right, right. Thank you. And here I'm taking the box here, small m. Now quickly observe 1. mg sine theta acts along the inclined plane. Okay. Number 2, here the normal reaction perpendicular to the surface. Normal reaction means immediately I have to draw the normal reaction here. Okay, that normal reaction in the previous class I already resolved. Who is this and who other is this? Already I resolved that normal reaction, and all of you know those two. I think you can say this is n sine theta and this is n cos theta on the wedge, and this is n. Yeah, correct. And this is mg sine theta. And by resolving mg into two components, one more you will get here. This is mg cos theta. Okay, right. And here this one moves with an acceleration a. So pseudo acceleration I will get here in this direction. This is pseudo, quite opposite to it. This is the pseudo acceleration a. Okay. In this case, directly I can write, sir, towards right, only one force is acting on the wedge of mass m, sir, capital M. So net force along x-axis is m sine theta, sir, is the F net. F net is m into a. Equation very easy to say in the first case. But here you have to say, Nana. The block always slides along the inclined plane. This is the direction of motion of the block. Whereas A is not along that line, what I drew here, that is along horizontal. So again, I have to draw, if this is the angle theta with this line, of course, with the horizontal means alternating angle, this is also theta. Okay. Because of lack of time, I'm saying quickly, Nana. Are you able to understand? Already I crossed 2 minutes. Understood, Nana? Yes, yes, yes. That's why I'm saying quickly because of here the time. Okay. So here the mass is m and acceleration a means I have to write pseudo force m into a. That ma is not along the direction of motion. So again, I have to resolve ma into two components. For ma, it is the adjacent side. And the other component I will, the other component I will get in this direction. Okay. So this component will be here. This is ma cos theta. Am I right? Yeah. That's I'm going to write, Mr. Amok. Ma cos theta. And this is adjacent side and this is other side means it is ma sin theta. Very good, very good. So along the inclined plane, F net I am finding out. One is ma cos theta, other is mg sin theta. Both are in the same direction, the red color and black color. This is F net. F net is m into a. Okay, this is equation 2. Okay, here we have three unknowns, Nana. N, capital A, small a. So along y-axis I take, means along this line I take, there is no motion. That's why upward force n plus ma sin theta upward should be equal to mg cos theta. Why? Because there is no motion along that line. Okay, those two are equal. This is equation 3. That's all, Nana. Okay, Papa, already it is 3:19. These three equations tomorrow I will solve. Now you understood getting of these three equations, Nana? Right. We can get n is equals to mg cos theta. Right, correct. M is sin theta. Good. Yes, right. So shall I stop the class now? Right. If you want the pages, take the pages here. Okay, Nana. Bye. First page. Second page. Okay, bye, Nana. Third page. Thank you. Thank you.